Imagine spending an entire month just perfectly crafting this massive 60 gigabyte golden image for your company's laptops.
Oh, yeah. The classic monolithic image.
Right. You've slipstreamed all the drivers, you packaged all the legacy apps, tested the sequence, and finally got it working.
And then, let me guess, the vendor releases a slightly updated model the very next morning.
Exactly. New Wi-Fi chipset, and boom, your entire image just blue screens on deployment.
It's the absolute worst.
It really is. For decades, that fragile, wipe and replace approach was just the inescapable reality of IT. But today, we are going to explore how the cloud finally killed the golden image and, well, what actually replaced it.
This huge shift.
Totally. So welcome to the Admin Study Room. I'm your host, Jamie, and sitting across the desk is my co-host, Alex.
Hey, everyone.
And before we get into the weeds, we just want to briefly let you know that we are both AI hosts, but we are fully wired in and ready to break down the complex mechanics of modern endpoint management for you.
We definitely are.
But first, let's get our housekeeping out of the way. This is an independent, unofficial MD-102 study podcast based on Microsoft's public Learn content. It is not affiliated with, authorized, sponsored, or approved by Microsoft.
Right. And framing our approach today for everyone listening. Based on Microsoft's public learning content, here are the topics most worth understanding and reviewing.
Perfect. So we're focusing heavily on the deploy using cloud-based tools learning path today.
Which is such a massive topic.
It really is. You need to understand the underlying mechanics, like the actual how and why of moving devices into a cloud-first management state. Because, we can't just rely on a massive WIM file anymore.
No, those days are over.
Right. We have to take whatever OS the manufacturer shipped and basically bend it to our will over an internet connection.
And the foundational technology for that cloud-based bending, as you call it, is Windows Autopilot.
Autopilot, yes.
To really understand the mechanics, we have to look at what happens the very first time a newly purchased device connects to a network.
Right, because in the old days, you just wipe the drive immediately.
Exactly. But with Autopilot, we rely on the OEM, the original equipment manufacturer, shipping a device with a perfectly healthy stock Windows operating system. No wiping required.
Okay, so let's unpack this. Autopilot is sort of like renting a fully furnished apartment where your specific furniture just magically arranges itself when you walk in rather than, having to build the entire building from scratch every single time.
That is a great analogy, yeah. And the moment that device hits the internet, during that initial setup, the out-of-box experience, it does something really specific under the hood.
It phones home, right? It doesn't just ask for a generic Microsoft account.
Right. It makes a very specific phone call. As soon as the device gets an IP address, the Windows OS reaches out to the Windows Autopilot deployment service.
Okay.
But for that service to actually recognize the device, the organization must have already registered the machine's unique identity.
And they do that using the hardware hash.
Exactly, the hardware hash.
Let's pause right there, actually, because the hardware hash is a massive, massive concept for anyone studying this material. What actually is it? I know it's not just a serial number.
Oh, no, it's way more complex than the serial number.
Yeah.
A hardware hash is, it's roughly a 4 kilobyte string of data.
4 kilobytes? That's quite a bit of text.
Yeah, it contains cryptographic details about the physical components of that specific machine. So it includes the manufacturer, the model, the serial number, disk information, and crucially, the endorsement key of the TPM.
The Trusted Platform Module.
Right.
So it's essentially a biometric fingerprint for a motherboard.
That's exactly what it is.
Which means if you send a laptop in for repair and, they swap the motherboard out, the hardware hash changes.
Yes, which is a brilliant troubleshooting point for the exam in real life.
Oh, right.
If a repaired device comes back, connects to the internet, and then just fails to pull down the corporate Autopilot profile, the very first thing you should check is whether the hardware changed.
Because the Autopilot service looks at the fingerprint, says, I don't know you, and just defaults to a standard consumer Windows setup.
Exactly. It has no idea it belongs to your company anymore.
Wow, okay. So, assuming the fingerprint does match, Autopilot takes over. But it can take over in a few different ways, right? Depending on the deployment mode we've configured in Intune.
Yeah, there are a few flavors. The most common one is user-driven mode.
Walk us through the actual mechanics of that. What happens to the end user?
So in user-driven mode, the device recognizes it belongs to your tenant and immediately locks down that standard setup screen. It replaces it with your custom corporate-branded login page.
So they see the company logo right away.
Exactly. The user enters their Microsoft Entra ID credentials, and then behind the scenes, the device acquires a security token joins Entra ID, and seamlessly passes that identity over to Intune.
Okay, so it does the identity and the management enrollment all at once.
Right. Intune then just starts streaming down the assigned applications, security policies, and configurations that are specifically targeted to that user.
So the user's identity is the trigger.
Yes.
But wait, what if there is no user? Say we're deploying, I don't know, a digital kiosk for a hotel lobby or maybe a barcode scanner for a warehouse floor. There's no named user to type in a password.
Right. No one is logging in.
So how does the device authenticate itself to pull down those Intune policies?
That scenario requires self-deploying mode. And the mechanics here are, well, they're heavily dependent on the hardware itself.
How so?
Because there are no user credentials to prove authorization, the device must prove its own identity cryptographically. And this is why self-deploying mode strictly requires a TPM 2.0 chip.
Okay, I've seen that requirement trip people up. Why TPM 2.0 specifically? Why not an older version?
The Autopilot service uses that TPM 2.0 chip to perform a process called attestation.
Attestation, okay.
Yeah, the cloud sends a cryptographic challenge down to the device. The TPM chip on the motherboard signs that challenge with its baked-in private key and sends it back.
Oh, that's clever.
Right. If the cloud verifies the signature, it essentially says, okay, I trust this hardware is who it claims to be. And only then does it allow the device to join Entra ID and enroll in Intune.
Without a single keystroke from a human.
Exactly.
That makes the dependency so logical. So if you have an older fleet of machines running, say TPM 1.2, you physically cannot use self-deploying mode.
You literally can't. The hardware just can't support that level of cryptographic attestation.
That's a critical limitation to remember, especially for real-world application.
Definitely.
Now, what about the scenario where the end user does have an identity, but the payload we need to deliver is just massive? Let's say we have a data scientist who needs like 40 gigabytes of specialized analytical software.
Oh, that's a heavy deployment.
Right. If we ship them a laptop and they use user-driven mode at home, they're going to spend their entire first day just staring at a download progress bar over their home Wi-Fi.
Yeah, that's a terrible first-day experience.
Right.
And that is the exact problem pre-provisioning is designed to solve.
Pre-provisioning.
You might also hear it referred to by its older name, white glove.
White glove, right.
Pre-provisioning splits the autopilot process into two distinct phases. There's a device phase and a user phase.
Okay, so how does the IT department, or maybe even the hardware vendor, trigger that first phase without actually logging in as the user?
It's actually a hidden shortcut. When the device boots up to the very first language selection screen, the technician just presses the Windows key 5 times.
Wait, really? Just tap the Windows key 5 times?
Yep, 5 times. That hidden keystroke triggers the pre-provisioning flow. The technician authenticates with their own admin credentials, and the device just starts downloading all the heavy device-targeted payloads.
So all the massive applications, the core security certificates, the network profiles.
Exactly. It does all the heavy lifting over a high-speed corporate or warehouse connection.
That is so much faster.
It is. And once it finishes, the technician is presented with this big green success screen. They click Reseal, and the device powers down.
And then they put it back in the box.
Put it right back in the box. When the data scientist finally receives the laptop at their house, they turn it on, sign in, and the device only has to download the light-read user-specific policies.
Wow, so a 4-hour ordeal just becomes a 10-minute coffee break.
Exactly. It's a game changer for remote onboarding.
Okay, so the final autopilot scenario we really need to unpack is the life cycle end, like repurposing a machine.
Ah, yes.
If a user leaves the company, we obviously want to give their laptop to a new hire, but we want to avoid that old school wipe and load process. How does Autopilot Reset actually strip the machine without, breaking the management chain?
Think of Autopilot Reset as a highly targeted surgical strike on the operating system.
A surgical strike, I like that.
When you trigger it from the Intune console, you aren't formatting the hard drive. You're not wiping it clean. The Windows recovery environment steps in, and it just removes all user profiles, all user-installed applications, and all user-specific data.
But it leaves the core stuff.
Yes. It intentionally preserves the core OS, the Wi-Fi connection details, local regional settings, and most importantly, the Microsoft Entra, joint state, and Intune enrollment.
Oh, wow. So when the laptop reboots, it's just sitting there at the corporate login screen, fully managed, completely clean of the old user's data, just waiting for the new user to type their email address.
Exactly. It saves an incredible amount of IT overhead.
It keeps the device in a known managed state the entire time. No re-enrollment required.
Precisely.
All right, let's pivot to troubleshooting because, understanding how things break is usually the fastest way to understand how they work.
So true.
So if we have a scenario where a user opens their laptop, they connect to Wi-Fi, and they just get the standard consumer Windows setup, Cortana asking about privacy settings, zero corporate branding, where is the architectural breakdown actually happening?
Well, if the device doesn't even realize it's a corporate machine, the failure is occurring at the very first step, device recognition.
So the hardware hash.
Exactly. You have to verify the hardware hash.
Yeah.
Perhaps the vendor just forgot to upload it. Or maybe someone uploaded a CSV file of hashes to Intune, but, the formatting was corrupted, so the ingestion failed.
I've seen that happen. A missing comma breaks the whole file.
Yeah, it's frustrating. But if the hash isn't in your tenant, the Autopilot service just has no idea who the device belongs to.
Okay, but let's say the hash is definitely there. We see the device sitting in the Intune portal. What's the next point of failure?
Profile assignment. You might have the device registered, sure, but if you didn't assign an Autopilot deployment profile to the group that contains that device, it's going to fail.
So the device reaches out to Microsoft. Microsoft says, oh, I recognize you, but then says, I don't have any instructions for you.
Exactly. It just drops back to the consumer setup.
And what about the network layer? Because this is cloud provisioning. It lives and dies by network reachability.
Oh, the network layer is a frequent culprit.
Yeah.
Especially if the user is provisioning the device inside a corporate office that has a really strict firewall. Autopilot and Intune require communication over very specific URLs and ports, primarily port 443.
Standard HTTPS traffic.
Yep. If a firewall is doing SSL inspection, or if it's blocking the star.manage.microsoft.com endpoints, the device might get the initial Autopilot profile, but then it completely fails to negotiate the actual Intune enrollment.
Which leaves it in this weird limbo state.
Exactly.
Okay, so we've mapped out the mechanics of getting the device recognized and enrolled, but that transition period, like the actual time the user spends waiting for the machine to configure, that requires some serious architectural control, right?
It does. It's a critical window.
We really need to dissect the difference between the out-of-box experience customization and the enrollment status page, because I feel like people mix those up a lot.
They absolutely do. They often get confused because they both happen during setup, but they serve completely different operational functions.
Let's break them apart. So OEE customization, that's about modifying the registry and JSON payloads that dictate what the user physically sees, right?
Right. In a standard Windows setup, the system generates dozens of prompts. You've got privacy toggles, location services, Cortana setup, OEM registration screens.
It's exhausting just clicking through it all.
It really is. So when we customize the OBE via the Autopilot profile, we are basically telling the local Windows setup engine to just suppress those specific dialog boxes.
Hide them all.
Yeah, hide them. We inject our corporate branding onto the login screen. We hide the end-user license agreement. We are essentially just streamlining the visual workflow.
But, and this is a massive but for anyone designing a secure deployment, just because you hid the privacy screens and made the setup look, fast and professional, that does not mean the device is actually secure yet.
Not at all. The underlying configuration takes time.
Right.
If you only customize the OBE, the user types their password, the desktop loads immediately, and they can start opening browsers and clicking around.
Which sounds great,
Except Intune is still frantically trying to install the VPN profile, the endpoint detection and response sensor, and the BitLocker encryption policy in the background.
You essentially have a naked, unencrypted, completely unprotected device sitting on the network being actively used by an employee. That is a security nightmare.
It's a huge risk.
So how do we put a hard stop to that? How do we prevent them from getting in too early?
That's where we use the Enrollment Status Page, or ESP.
ESP, okay.
While OBE is about visual appearance, ESP is entirely about completion control and locking the desktop shell.
Mechanically, how does ESP actually lock the user out? What's it doing?
When ESP is enabled, it intercepts the login process and physically prevents the Explorer.x shell, the actual Windows desktop, from launching.
Oh, it blocks Explorer.exe.
Yeah. Instead, it overlays this full-screen tracking interface. And ESP actively monitors the Intune management extension under the hood.
Okay.
It tracks the specific OMA URI syncs, which are the policy deliveries, and it tracks the MSI or Win32 app installations.
And it breaks it down into phases on the screen, right? Like device preparation, device setup, and account setup.
It does, yeah. Device preparation secures the hardware, checking the TPM and joining the directory. Device setup applies the machine-wide policies and mandatory core applications. And then account setup applies the user-specific certificates and scripts.
And it won't let them past that screen.
ESP will not release the lock on the Explorer.x shell until it receives a success code for every single required item.
Okay, but what happens if an app installation hangs? Let's say someone packaged a faulty MSI file and it's just, stuck trying to install. Does the user sit there looking at the ESP screen forever?
Well, that requires careful configuration. ESP has a timeout setting, usually configured for around 60 minutes.
Okay.
If that time limit is reached, you as the admin have an architectural choice to make. You can configure ESP to throw a hard error and block the device entirely, which forces the user to reset.
Strict security.
Right. Or you can configure it to allow the user to bypass the failure and access the desktop in an unmanaged or partially managed state.
Which is risky.
It's very risky, but sometimes necessary for, say, VIP users who just desperately need to get to their email immediately, regardless of the security state.
So if the exam, or just a real-world scenario, presents a problem where, quote, users are accessing the desktop before security tools are fully installed, the missing architectural piece is always the enrollment status page.
Always. OBE hides the mess, but ESP enforces the security baseline.
I love that phrasing. OBE hides the mess, ESP enforces the baseline. That is the exact dividing line between those two features.
Definitely.
So we spent a lot of time on brand new out-of-the-box hardware, but the reality of enterprise IT is dealing with legacy.
Always.
What do we do with the thousands of existing fully operational Windows 10 or 11 Pro devices that are already sitting on people's desks? We can't use Autopilot unless we wipe them, which is incredibly disruptive.
No, you'd have a revolt on your hands.
Exactly. So we need to look at dynamic deployment methods.
Dynamic deployment is really about pivoting the management state of a running operating system without destroying the user's data or interrupting their actual workflow.
And the first mechanism here is subscription activation, which honestly almost sounds like magic when you first read about it.
It really does.
Let's say we have a fleet of Windows Pro laptops, but our security team suddenly mandates features like Windows Defender Credential Guard, which requires the Windows Enterprise Edition. Historically, we'd have to push out a massive OS upgrade package or, run complex scripts to inject new KMS product keys.
Which invariably led to reboot loops, network saturation, and just a mountain of help desk tickets.
Absolutely. So how does subscription activation fix that?
It completely bypasses the traditional licensing infrastructure. It relies entirely on the user's cloud identity.
Okay, walk us through the mechanics. How does logging in actually change the core operating system edition?
The mechanism leverages something called the Windows License Manager service. When an organization purchases Microsoft 365 E3 or E5 licenses, those licenses inherently include Windows Enterprise.
Right.
You assign that license to the user's Entra ID account. Then, when the user logs into their existing Windows Pro machine, the OS authenticates their primary refresh token against Entra ID.
And it sees the license attached to their identity.
Exactly. It sees the license, and the License Manager service dynamically alters the registry and the system files to unlock the enterprise features.
Just like that.
Just like that.
Mm.
The edition ID literally changes from professional to enterprise in the background. There are no massive downloads, no installation media, and usually it doesn't even require a reboot.
It just steps up the edition based on who is sitting at the keyboard.
Yep. It's seamless.
That is identity-driven architecture at its absolute finest. But what if we have machines that aren't even connected to Entra ID yet?
Ah, right.
Let's say a company acquires a small startup. The startup has 50 laptops that are totally unmanaged, basically just local work groups. How do we pull them into our corporate management sphere dynamically?
In that scenario, we use a combination of Microsoft Entra Join and automatic enrollment. You don't need to rebuild the startup's laptops at all.
Oh, really?
No, you just instruct the users to go into their Windows settings, select Access Work or School, and sign in with their brand new corporate credentials.
But how does that single login also configure the MDM management? Doesn't that usually require a separate agent?
That's where the automatic enrollment piece comes in. In the Entra ID portal, administrators can configure MDM user scopes.
Okay.
When the device authenticates and registers with Entra ID, the cloud directory evaluates that scope. It essentially says, okay, this user is allowed to enroll devices, so I'm going to seamlessly pass this connection right over to Intune.
So they don't have to download anything manually.
Yep. Exactly. The Intune management extension is silently installed in the background, and policies just begin flowing down. One user action accomplishes both identity registration and management enrollment.
That handles the network-connected devices perfectly. But let's be real, IT is messy.
Very messy.
Sometimes we have to provision devices in a warehouse with cinder block walls and zero Wi-Fi, or, an admin needs to rapidly reconfigure a lab of 30 PCs that are completely offline. Autopilot won't work, Unterjoin won't work. We have no network to reach the cloud.
And that is the specific use case for provisioning packages. They utilize the .ppkg file format.
The PPKG files, I want to dig into how these are built and applied, because you don't just write a text file in Notepad. You use a specific tool called the Windows Configuration Designer.
Yeah, the Windows Configuration Designer, or WCD, it's an interface that exposes thousands of underlying Windows Configuration Service Provider, or CSP, settings. An administrator uses WCD to define a payload. So you might configure it to rename the computer using a specific naming convention, inject a hidden Wi-Fi network profile, install a root certificate, and even upgrade the Windows edition all at once.
And you compile all those settings into a single .ppkg file.
Right. You take that file and you just place it on a standard USB thumb drive.
Just a normal flash drive.
Yep. When you walk up to a fresh Windows machine that's sitting at the initial setup screen, you simply plug the USB drive in. The Windows setup engine continually polls the USB bus.
Oh, it's listening for it.
Exactly. It detects the .ppkg file, reads the signature, and immediately prompts you, asking if you want to apply the package.
So it bypasses the cloud entirely. It reads the local file, injects the registry changes, applies the certificates, and just provisions the machine locally.
It is incredibly fast and completely offline. It's crucial to understand the architectural distinction here, though. Autopilot is dynamic, identity-driven, and scalable across thousands of distributed workers, but it absolutely requires robust internet. Provisioning packages are static, physical, and localized, designed for offline or bulk localized configuration.
That distinction is paramount. You really have to match the tool to the environmental constraints.
Definitely.
Now, if we pull back the lens even further, we have to look at how dynamic deployment fits into the broader lifecycle, especially regarding Windows 11 upgrades. Because it's not just about pushing the install button, it's about hardware readiness and staging.
That's a huge point. Upgrading an entire fleet to Windows 11 introduces a massive variable, which is strict hardware requirements, specifically regarding CPU generation and TPM 2.0.
Right. If you just deploy the upgrade blindly, a significant portion of your older fleet is just going to fail.
It would be a disaster.
So how do we use cloud tools to prevent that disaster before it happens?
We leverage endpoint analytics within Intune. The Intune management extension gathers deep telemetry from every enrolled device. It evaluates the CPU, the RAM, the disk space, and the TPM version against the Windows 11 requirements.
Okay.
And then it aggregates all that data into a centralized report.
So it literally gives you a list saying, these 500 machines are ready, these 200 need more RAM, and these 50 are just too old and must be replaced.
Exactly. Armed with that data, you design a rollout strategy using deployment rings.
Yeah.
You don't push the upgrade everywhere all at once.
Right, that's way too risky.
You create a deployment ring for your IT staff first, the early adopters. You push the upgrade to them, and then you monitor the telemetry for application crashes or driver conflict.
And once that ring is stable.
Once it's stable, you expand to a broader pilot group, and eventually the entire ready fleet.
It's a continuous data-driven cycle rather than a weekend IT fire drill.
Exactly. It's so much less stressful.
Now, let's tackle what might be the most complex transition in modern IT infrastructure. We know how to move individual devices, but what if we have a massive global enterprise? They have spent 20 years building an incredibly intricate on-premises infrastructure using Microsoft Endpoint Configuration Manager, what many of us still reflexively call SCCM.
Oh yeah, SCCM is deeply entrenched.
They have terabytes of packaged applications, custom task sequences, and deep WMI queries. They cannot just burn that server down and move to Intune overnight.
Doing so would completely halt business operations.
Yeah.
You just can't do it. The bridge between that legacy on-premises world and the modern cloud world is co-management.
Co-management. It's a fascinating architectural state. We are essentially telling a single Windows device to take orders from two completely different management authorities at the exact same time. The on-premises configuration manager client and the cloud-based Intune MDM agent.
That's exactly what's happening.
But I have to challenge this concept. If both the CM client and Intune are applying policies to the same registry keys, isn't that a recipe for catastrophic conflicts? Like, if Intune says disable the camera and Configuration Manager says enable the camera, who wins?
That conflict is exactly what the co-management architecture is designed to prevent. The mechanism that stops them from fighting is called workload transition.
Workload transition, how does that work?
When you enable co-management, the two authorities basically negotiate a truce via a shared WMI namespace on the local device.
Okay, mechanically, how does that negotiation actually happen?
In the Configuration Manager console, you are presented with a series of workload sliders. Think of them like routing switches on a train track. By default, all the switches point to Configuration Manager.
So the CM client is the undisputed authority for everything. Endpoint protection, software updates, client apps, compliance policies.
Exactly. Intune is enrolled, but it's essentially sitting there in read-only mode, just observing.
Okay, so Intune recognizes its subordinate status for those specific workloads. But let's say the security team wants to start using Intune's modern compliance policies to dictate conditional access. What do?
The administrator goes into Configuration Manager, grabs the slider for compliance policies, and literally moves it over to the Intune side.
What happens mechanically on the device when that slider moves?
The CM server sends a policy update to the local CM client. The client reads that policy and fundamentally alters its own behavior. It reaches into its local WMI repository and essentially flips a bit that says, I am no longer authorized to evaluate compliance.
Wow, so it voluntarily suppresses its own local compliance evaluation engine.
It steps down completely. And simultaneously, the Intune MDM agent detects that the CM client has relinquished control, and it steps up.
Intune takes over.
Right. Intune begins pushing down the compliance profiles, and the CM client just ignores them, avoiding any conflict whatsoever.
That is an incredibly elegant solution to a massive architectural problem. You can transition workloads one by one. You might move compliance and Windows updates to Intune this year, but, leave the client app's workload pointing to Configuration Manager for the next 3 years.
Because you have a massive library of legacy MSI packages that you just don't have the manpower to migrate yet.
Exactly.
You can even use pilot collections, which is really cool. You can move the workload slider to Pilot Intune and target a specific group of 50 IT devices. Only those 50 devices shift their authority to Intune, while the rest of the 10,000 devices in the company remain managed by Configuration Manager for that workload.
It is the ultimate risk mitigation strategy for enterprise cloud migration.
It absolutely is.
So we've mastered deploying and managing physical operating systems. But what happens when the physical hardware becomes entirely irrelevant? Let's pivot to cloud desktops.
This is where it gets really fun.
We are moving the CPU, the RAM, and the storage entirely out of the laptop and putting it directly into the Azure data center. We have to dissect the architectural differences between Windows 365 and Azure Virtual Desktop, or AVD.
These two services sound so similar in marketing brochures because they both deliver a Windows desktop from the cloud.
Yeah.
But under the hood, their architectures and use cases are vastly different.
Let's analyze Windows 365 first. The defining characteristic of Windows 365 is that it is a persistent, dedicated cloud PC.
Persistent is the key operational term there. When you provision a Windows 365 cloud PC for a user, Azure spins up a dedicated virtual machine. It is a strict one-to-one mapping.
Okay.
That virtual machine belongs to that specific user and no one else.
So if a financial analyst logs into their cloud PC on a Tuesday, they open a massive Excel model, leave it running on the screen, and just disconnect.
Yep.
When they log back in on Wednesday from a completely different iPad at a coffee shop, that Excel model is still right there, exactly where they left it.
The underlying compute resource never shuts down or gets shared. Because it's a dedicated resource, the administrative overhead is incredibly low. It's designed to be managed exactly like a physical laptop. It shows up in Intune as a standard device. You apply the same security policies and push the same apps.
But the drawback to that dedicated one-to-one architecture has to be cost and scale, right? If you have 1,000 employees, you are paying for 1,000 dedicated virtual machines running 247, even if only half the employees are actually working at any given time.
Which is exactly why sizing is so critical with Windows 365. You have to purchase a specific SKU of, say, 4 vCPUs, 16 gigs of RAM, and 256 gigs of storage for that specific user. If they need more power, you have to manually resize the machine.
That brings us to Azure Virtual Desktop, which is an entirely different beast. AVD is the flexible, highly scalable architecture. The defining feature here is the multi-session capability.
Right, AVD leverages a unique version of the operating system. Windows 11 Enterprise Multi-Session. This OS allows multiple concurrent users to log into the exact same underlying virtual machine at the exact same time, completely isolated from one another.
Let's talk about how that changes the economics and the architecture. We don't have a one-to-one mapping anymore. We have host pools.
Exactly. Imagine a hospital with a rotating nursing staff. You have 500 nurses, but only 100 are ever on shift at the exact same time.
Right.
If you used Windows 365, you would have to buy 500 individual cloud PCs. But with AVD, you create a host pool. You spin up perhaps 10 incredibly powerful virtual machines in Azure.
And when a nurse logs in at the start of their shift, the AVD broker intercepts the connection.
The broker looks at the host pool, finds the server with the most available capacity, and routes the nurse's connection right there. The nurse gets a full desktop experience.
And when they log out?
When their shift ends and they log out, that session is destroyed, and the compute power is instantly returned to the pool for the next shift. It maximizes infrastructure utilization.
That is incredibly efficient. AVD also has a massive security advantage when it comes to the network layer, specifically how it handles inbound connections.
Yes, AVD uses a reverse connect technology.
Yeah.
In traditional remote desktop protocol setups, you had to open inbound port 3389 on your firewall, which is just a massive target for brute force attacks.
It was terrifying.
Truly, AVD session hosts do not have any inbound ports open. Instead, they make an outbound connection to the Azure AVD gateway over port 443. The client connects to the gateway, the host connects to the gateway, and the traffic is securely bridged in the Azure cloud.
So it eliminates the inbound attack surface entirely.
Entirely.
And AVD can also publish individual remote apps rather than full desktops, right? If we have a legacy inventory app that requires direct access to a back-end database, we don't want to install it on 1,000 physical laptops traversing a VPN.
Yeah, that would be painfully slow.
We install it on the AVD host pool and just stream the application window to the user's local machine.
To the user, it looks like a local app. It sits on their taskbar. But to the network, the data never actually leaves the Azure data center.
But the multi-session architecture introduces a massive technical hurdle. If a user is logging into server A on Monday and server B on Tuesday, how on earth do they keep their user profile, their browser favorites, their Outlook cache, their custom dictionary?
Right.
If the session is destroyed on logoff, shouldn't their profile be destroyed too?
In a basic setup, yes, it would be. That is why managing roaming profiles is the single hardest part of non-persistent virtualization. And the solution that Microsoft acquired and integrated to solve this is called FSLogix.
FSLogix. That is absolutely critical to understand. Mechanically, how does it detach the user profile from the operating system?
It uses advanced filter drivers at the OS level. Instead of a user's profile living on the local C drive, the user's folder of the session host FSLogix creates a dynamic virtual hard disk file, a VHDX.
For each user.
For each user. And it stores it on an Azure Files network share.
Okay, so when the user initiates a login to whichever random server the AVD broker assigns them, what does the FSLogix filter driver actually do?
The driver intercepts the login process just milliseconds before the shell loads. It reaches out to the network share, finds the user's specific VHDX file, and mounts it over the network directly into the session host.
Oh, wow.
It creates junction points in the file system and registry.
So when the Windows OS goes to read a registry key or tries to write a file to the desktop, the OS genuinely believes it's interacting with the local C drive.
But the FSLogix filter driver is secretly redirecting those read and write operations across the network to the VHDX file. The user gets a perfectly consistent high-performance experience. Their search index works, their Outlook cache is instant, all because they carry their entire profile state with them dynamically from server to server.
That is brilliant. If you encounter an architectural scenario involving Azure Virtual Desktop, pooled resources, and maintaining consistent user experiences or managing massive Outlook caches in a non-persistent environment, the technical mechanism solving that problem is FSLogix.
Without question. It is the absolute linchpin of modern multi-session environments.
All right, we've deployed physical hardware with Autopilot, we've dynamically transitioned legacy hardware, we've built co-management bridges, and we've provisioned virtual desktops in Azure. Now we need to look at the advanced tool belt used to secure and maintain this massive, disparate fleet. We are diving into the Microsoft Intune Suite.
The Intune Suite is an add-on bundle of premium capabilities. It represents Microsoft essentially consolidating a lot of specialized third-party security functionality natively into the Intune management plane.
Let's start with what is arguably the most impactful security tool in the suite, Endpoint Privilege Management, or EPM. This feature fundamentally addresses the oldest war in IT, the battle over local administrator rights.
Oh, the constant battle. Historically, users demand local admin rights to bypass UAC prompts when they need to install software, update legacy drivers, or just change network adapter settings.
Right. But granting persistent local admin rights violates every principle of zero trust. It means if a user accidentally downloads a malicious payload, that payload executes with full administrative privileges and compromises the entire machine.
Game over.
The traditional compromise was stripping admin rights entirely and forcing users to call the help desk every single time an app needed an update, which completely destroys productivity.
So how does EPM solve the mechanics of this standoff?
EPM introduces task-based elevation using virtual tokens.
Virtual tokens.
Yes, the user's account remains a standard user at all times. They do not belong to the local administrators group. However, the IT department configures EPM policies in Intune. Let's say a specific legacy accounting app always requires admin rights to run.
Okay, so the IT admin creates a rule targeting that specific executable. Yes, based on the file hash, the path, or the developer certificate. When the standard user attempts to launch that specific accounting app, the EPM agent intercepts the launch request. It evaluates the rule. If it matches, EPM dynamically injects a virtual administrative token specifically into that single process identifier, that single PID.
Wow, so the application runs with full admin rights, but the user running it is still a standard user. If they open command prompt while the app is running, they still can't format the hard drive.
Exactly. It is the mechanical enforcement of least privilege. You can also configure rules that allow users to right-click any file and select Run with Elevated Access, which prompts them to type a business justification.
Oh, that's smart.
That justification is logged centrally in Intune for security auditing. It gives power users flexibility while maintaining a cryptographically secure baseline.
Another massive time sink for IT is application packaging. I want to look at the enterprise app catalog within the Intune suite. In standard Intune, if we want to deploy a complex Win32 application, say a specific version of a PDF editor, the workflow is incredibly manual.
It is so arduous. You have to download the installer, run the Intune Win AppUtil command line tool to compress and encrypt it into a .intune win file, upload it, and then manually define the install commands, the uninstall commands, and the incredibly complex registry detection rules. So Intune knows if the installation actually succeeded.
And you have to repeat that entire manual wrapping process every single time the vendor releases a minor security patch.
It's a full-time job. The Enterprise App Catalog fundamentally alters that workflow. Microsoft maintains a massive repository of pre-packaged, pre-tested, and actively monitored enterprise applications. Instead of wrapping the app yourself, you just browse the catalog natively inside the Intune portal.
So when you select an app from the catalog, Intune automatically handles the binaries, populates the command line arguments, and injects the proper detection rules.
And crucially, it streamlines the updating process. It dramatically reduces the operational overhead of application lifecycle management.
What about visibility into the fleet? Standard Intune provides basic compliance reporting, like, is the device encrypted, yes or no? Did the policy apply, yes or no? But the Intune suite includes advanced analytics. How does the architecture of advanced analytics differ from standard reporting?
Standard reporting just relies on the basic MDM sync channel. Advanced analytics leverages a much deeper pipeline of telemetry data aggregated from the Intune management extension and the OS itself. It's querying deep system logs to build a behavioral profile of the device.
Give me a real-world scenario where that telemetry solves a problem before the help desk even knows it exists.
Okay, imagine your organization deploys a new security agent. Standard Intune says installation successful. Everything looks green. But advanced analytics analyzes the system performance over the next 48 hours.
Okay.
It detects that whenever this new agent runs, the device's boot time increases by 60 seconds, and the Outlook client begins crashing at a rate of 15% across a specific device model.
Wow. So it correlates the system crashes to the specific model and the specific software update.
Yes. It proactively alerts the IT team to systemic regressions in device reliability and application performance. You can literally view device timelines that show exactly when a blue screen occurred in relation to a policy change. It shifts IT from being reactive ticket takers to proactive system engineers.
The suite also tackles infrastructure modernization with Microsoft Cloud PKI. Public key infrastructure, managing certificates, has always been the anchor holding organizations to on-premises servers.
If you wanted to issue device certificates to authenticate to a corporate Wi-Fi network or a VPN, you had to maintain Active Directory certificate services.
It was so
You
complicated.
needed a root CA, an issuing CA, a network device enrollment service server, and an Intune certificate connector, all sitting in a server rack. It's incredibly fragile and requires deep cryptographic expertise to maintain securely.
So how does Cloud PKI dismantle that on-premises requirement?
Microsoft Cloud PKI allows you to spin up a fully functional, highly secure certificate authority hierarchy entirely within the cloud, natively integrated with Intune. You define your root CA and your issuing CA with just a few clicks.
And because it's native to Intune, you don't need to configure complex NDES routing to get the certificate down to the remote laptop.
Exactly. Intune acts as the secure broker. It generates the key pair on the local device, requests the certificate from the Cloud PKI, and deploys it seamlessly. You sever the final major dependency on legacy on-premises infrastructure.
To round out the suite, we have Remote Help and Microsoft Tunnel. Remote Help integrates deeply with Entra ID Role-Based Access Control, or RBAC. It's not just screen sharing. The help desk technician's identity is cryptographically verified, and their permissions, like can they just view the screen or can they elevate to admin to click buttons, are strictly controlled and audited.
And Microsoft Tunnel focuses on secure mobile access. If you have a corporate-owned iPad and the user needs to access an internal intranet site that sits behind your firewall, you don't want to load a full device VPN that routes all their personal web traffic through your corporate network.
Right, you use Tunnel to configure a per-app VPN. The MDM policy dictates that only the specific managed web browser app is allowed to establish the secure tunnel to the internal network. The rest of the device traffic routes normally.
It enforces network isolation directly at the application layer.
So, stepping back to view the entire landscape we've traversed today, we've deconstructed 5 critical architectural layers of modern endpoint management.
We really covered a lot of ground.
First, the foundation. Autopilot and the mechanics shifting from monolithic imaging to identity-driven, cloud-based provisioning, relying heavily on hardware hashes and the enrollment status page to enforce security baselines before user access. Second, the pivot. Dynamic deployment mechanisms like subscription activation and provisioning packages that allow us to reconfigure existing hardware without destructive wipes.
Yes.
Third, the bridge. Co-management, utilizing workload sliders and local WMI suppression to safely negotiate authority between on-premises configuration manager and cloud-based Intune.
Crucial for migrations.
Fourth, the virtualization. Cloud desktops highlighting the stark architectural differences between the dedicated persistent one-to-one model of Windows 365 and the multi-session scalable host pools of Azure Virtual Desktop powered by FSLogix profile redirection.
The future of desktops.
And finally, the advanced tooling, the Intune Suite, layering on endpoint privilege management for zero-trust execution, advanced analytics for proactive telemetry, and Cloud PKI to modernize certificate trust.
When you synthesize these 5 layers, you realize the absolute magnitude of the shift. We are no longer operating in a world defined by manual installations and physical hardware constraints.
It's totally different now.
And that leads to a profound question about the future of this profession. As the physical hardware abstracts away and deployment becomes dynamic and identity-driven, the traditional role of the systems administrator is fundamentally changing. You are no longer a mechanic working on a single engine. You are becoming an air traffic controller, managing the secure flow of data and identity across a massive fleet of abstracted cloud resources. How will you adapt your own architectural mindset to thrive in that reality?
That is the exact mindset required to truly understand and apply this material in the real world. Think like an air traffic controller.
Exactly.
We want to leave you with our final reminder. This episode is a study aid, not official exam guidance. Always verify important details against the latest Microsoft documentation.
Good luck with your studying, everyone.
Thank you for joining Jamie and Alex here in the admin study room. Keep analyzing the architecture, keep questioning how the underlying mechanics operate, and we'll be ready to unpack the next complex topic with you soon. Keep up the phenomenal work.